We'll start our morning lecture by Daniel, which is inflation in string theory. This will be the last lecture, so ask as many as questions you have now as well as in the discussion session. Daniel.
Okay, thank you very much. Yeah, so welcome to this last lecture. So yesterday we finished off, I showed you a little bit about the UV sensitivity of inflation. And so sometimes this UV sensitivity, sometimes this UV sensitivity is described as a problem for realizing inflation in fundamental physics. But I think it's worth realizing that for people who have an affinity for quantum gravity, of course, we should view this as an opportunity. Okay? It's an opportunity because it's one of those rare examples where you're sensitive to very high scales, and it would be sad if every phenomena were to completely decouple from those interesting effects at high scales. So sometimes people think maybe this is a window into quantum gravity by studying inflation in this context. So I want to describe to you a little bit what inflation in string theory is all about. It's a bit dangerous to do this in one lecture, and I worry about it. The reason I worry about it is that if I'm trying to do too much in one lecture, and I'm looking at my slides, I think I'm trying to do a little bit too much, you might get away with the impression that everything is done a little bit schematically, because I have to inevitably, simplify a few things and just, give you the basic structure of things. So my excuse is that you can look at our review, and we put everything we know about the subject somewhere in these pages. And so there are lots more details. So if you think, things are done not rigorously enough, and so check there, and if you then still think things are not rigorous, then email me and we can discuss. Things certainly won't be done rigorously enough in these slides now. That's just because I have 60 minutes, and even that's not quite enough. Okay. In fact, actually, if you remember this website that I gave you, Puri.pdf, little trick: if you change Puri.pdf into Amsterdam.pdf, yeah, you'll get a version of this where I basically spend 6 hours doing the same. There's some handwritten lecture notes where a lot of the gaps that will appear here are filled in. So you can use that to get a little bit more information if you don't want to bother, going straight into this longer treatment. Okay? So my plan today is basically do 3 things. First, I want to just connect a little bit string inflation to what we said yesterday. So we were talking about effective theories with some unknown high scale. In string theory, that unknown high scale becomes a physically motivated scale, or several physically motivated scales. I want to describe this a little bit. So that will just give you as a broad frame of mind of how to think about what we're then going to see in specific examples. Then we're going to see that one of the basic challenges is to do simultaneously as the stabilization of the moduli that arises when you try to describe four-dimensional physics with inflation. Early in the history of the subject, people thought these 2 things can be done separately. Now we understand very well that that's not the case. You really have to do everything at once, especially precisely because of this UV sensitivity. You cannot just freeze the moduli separately and ask questions about inflation in a modular way. No pun intended. Okay, and then finally, if I have time, I want to go through 2 examples in a little bit of detail. We will see how much time I have, and maybe I have to choose one of the 2. And if people want to know about the other one, we can. You can ask me separately. But maybe I do have time. I have no sense how long this will take. Okay? Okay, so let me start. So first I want to basically connect string inflation to what we said yesterday. So this is a simple equation that summarizes what this whole business is about, of course. So we start from a theory, string theory, that is naturally defined in higher dimensions, 10 dimensions. It's defined in terms of some discrete compactification data, some discrete statements about the topology, geometry, discrete quantized set of fluxes, and then maybe some local sources, which are D-branes and orientifold planes. Okay, that's how our theory in the UV is defined. And then we want to describe this theory in the IR, but more than that, we want to compactify the theory to 4 dimensions. Okay, so we want to describe that theory on for example, a product space of 4 large dimensions and 6 small ones. Okay. And as you, of course, know, when you do that compactification, you get extra fields in the 4-dimensional effective theory. And so our goal is to do this compactification and describe the 4-dimensional effective action that arises from this. Okay? And so with some luck, you will then have scalar fields or other types of fields with energy densities that are slowly evolving. Or you can ask, what kind of conditions have to hold in this this more fundamental theory that this some inflationary dynamics arises. Okay. But first, I want to talk a little bit about the structure of this for the effective action that you can expect from this procedure, without going into details, and then we will see in examples how this actually happens. Okay. So the first thing we can ask, of course, about effective theory is what are the relevant energy scales? Okay. What are the scales where new degrees of freedoms might become important, or couplings to higher scales become important? So it's important to have this in mind so that we can formulate our effective description. So the first scale, of course, that is important is typically the scale of our experiment. Okay? So in particle physics, this would be the center of mass energy, for example, of our collider. And so I mentioned this already yesterday in the discussion session, I think, that for inflationary observables, or for the CMB, for example, we're measuring all of those fluctuations when they cross the horizon, when the frequency is of order the Hubble scale. That's when they're frozen in. And so it's this curious situation where we have a single energy experiment. Yeah? So the cosmos has provided us with a single energy experiment. We can never change it. Yeah? So we can never actually increase the center of mass energy of our universe experiment in that sense. Okay, so all we can ever hope to do with measurements is to do precision measurements. Yeah? It's like if you were stuck with LEP, yeah, as a collider forever, for eternity. The only way you can learn about high-scale physics is by measuring more and more precisely, high dimension operators, for example, those kind of things. Yeah? Because you can never actually raise your energy to produce these heavy states, but you maybe can indirectly infer their existence from measuring processes very precisely. So we're always in the situation where we're doing precision measurements, okay? And I've showed you how Planck is providing us with these very precise measurements of non-Gaussianity and those kind of things, okay? Okay, so that's an important scale, and then we can ask what happens if we, for modes that are at higher energies or lower energies, and of course that's what separates superhorizon from subhorizon. So frequencies lower than this scale Hubble are outside of the horizon, frequencies higher than Hubble are inside of the horizon. Okay? So that's the first scale that we have. A second scale that we have when we then try to formulate this in string theory, of course, is the string scale, okay? Given here in terms of alpha prime. Again, we can ask what happens at energies above or below the string scale, and of course, you know that at energies below the string scale, we can describe it as an effective supergravity, okay? While at energies above the string scale, we have to include the massive tower of string states, and we have to describe the dynamics fully non-perturbatively in string theory, okay? So that's an important threshold where our description changes. And most inflationary models are formulated in the regime where the Hubble scale is below the string scale, such that it reduces to an effective supergravity. Okay, that's not absolutely necessary, but we have very little tools to do anything other than that. Otherwise, if the Hubble scale were above the string scale, it would mean that when we're computing CMB observables, we would have to do that in string theory. There's no supergravity approximation to that calculation. Yeah? And conversely, because we're always formulating things in the regime where things reduce to an effective supergravity, and often this Hubble scale is chosen to be much less than the string scale, it's also natural to expect that very stringy effects will decouple just by the usual logic of effective theory, okay? There's a suppression parameter of stringy effects that is h over m string to some power, okay? So it's not so surprising that in the end of the day, we will have to search hard for very stringy effects because we're not really exciting string modes very, very directly during inflation, okay? If you have some extra tools in your pocket that you're currently developing that allows you to do anything in a more extreme regime, that would be very interesting, okay? Yeah. That's true. Very good, yeah. Yes. And I can give, we can talk about examples for that. So for example, Maldacena recently was deriving a symmetry-based constraint on the 3-point functions of gravitons during inflation that holds to all orders in alpha prime, for example, or yeah. So it would hold even if your theory of, even in that regime, or if you have higher curvature correction, higher alpha prime corrections to Einstein-Hilbert and stuff like that. So that's true. To scalars, you guys have done that for scalars. Yeah, exactly. Okay. Very good. So you do have a toolkit. So small tool, yeah. Okay. And another important scale, especially when we're talking about compactifications, is the Kaluza-Klein scale. Okay. So that's the scale associated with the inverse size of the compactification. And here again, how do we distinguish the regime above and below the Kaluza-Klein scale? Of course, at energies below the Kaluza-Klein scale, we're describing things in terms of an effective four-dimensional theory, while at energies above the Kaluza-Klein scale, we're really feeling the effect of the extra dimensions, and we have to describe things 10-dimensionally. And again, typically, the inflationary scale is chosen to be below the Kaluza-Klein scale, which therefore it isn't surprising that we're reducing to 4D effective theories of inflation, because we're already putting ourselves into that regime. Yeah? While but it would be interesting. There's nothing that says that this is absolutely necessary. You could try and play the game of having this Hubble scale be above the Kaluza-Klein scale, which then means you have to describe everything in a higher dimensional context. I don't know what would happen to the horizon problem. I don't know what happened to the scale invariance of the fluctuations and those kind of things. Scale invariance is tied to a little bit to, because then later you of course want to reduce to some four-dimensional physics. So if you have inflation happening or whatever type of dynamics you wanted to consider in 10 dimensions and you then reduce to 4 dimensions, you have to match the fluctuations from the 10-dimensional evolution to 4 dimensions. Whether that preserves scale invariance or not, interesting things to play with. I'm just saying this is the usual hierarchy that we're usually working with. Okay, and of course there's this relationship also between the string scale and the Kaluza-Klein scale in terms of the dimensionless volume of the compactification, so the volume in string units. And in order to have control over our classical geometry, this has to be a number bigger than 1, which then implies that the Kaluza-Klein scale is a scale below the string scale. So that's why these scales are ordered in the way I've shown it. Okay? Yeah?
Is that the case? Suddenly digital 6-dimension appear, or from 4 to suddenly 10-dimension appear. Is that the point? For example, what I want to ask is, maybe just 1 dimension appear.
Oh.
Is that the possibility? For 6 dimensions, concurrently appear?
Yes. Okay, I see. Well, I think when I'm saying 4 to 10, I indirectly assume that I'm having an isotropic compactification, where all the directions basically associated with the same length scale and same. In principle, of course, you could have some anisotropic compactification with several scales, and then you could excite those scales one at a time. And indeed, I think it would look of different dimensionalities would appear in the spectrum at different times. So isotropic, yeah. Yes. Yeah. Yeah, it'd be interesting what happens if you do something very, very anisotropic. Then, okay. Yeah, I should check when in these slides. Sometimes I'm going to assume isotropic. We're going to see when that happens. But as you also can see from this, the lowest KK scale is the one that's most relevant for us because that's the, okay, and then finally we have the Planck scale, and there's this relationship that you can derive between, and we can derive it later, in fact, between the string scale, the Kaluza-Klein scale, and the string coupling. In the regime of control, or at weak coupling, and for large volume in string units, all of these scales are smaller than the Planck scale. The Planck scale is the highest of. So if you're perturbatively complete gravity, then Planck scale is the last scale you would be hitting. And okay, and then the energies below the Planck scale, we can do perturbative quantum gravity, as Leonardo and I were saying yesterday. While at energies of order the Planck scale, you have to non-perturbatively complete the theory. Or you have to have new degrees of freedom, like in string theory, that appear before that and change our view on quantum gravity. Okay. Okay. So, and then finally, there's of course the 10-dimensional theory is described in terms of or has supersymmetry. The question is at what scale is that supersymmetry broken when we try to describe our 4-dimensional effective theory. And here we have a little bit of a, so I'm usually going to assume that this explicit SUSY breaking scale is the lowest of all of these scales, yeah? Which means that during inflation, we have positive vacuum energy, so it spontaneously breaks supersymmetry, but only spontaneously, yeah? So we still have a framework, a Lagrangian, that is dictated by supersymmetry constraints, and so we have some control over our calculation given by this underlying supersymmetry. But that, I should emphasize, that's really just a choice of you know, a wish for control over our calculation. It's a lamppost that we go to so that we can have more control over our calculation. That's not something that nature has dictated for us. And so at some point we have to break SUSY. For now, I'm going to assume that's going to happen after inflation. Okay. If the SUSY breaking scale is at the higher scale, we have more trouble actually describing compactification and moduli stabilization and all those things. Okay. But one has to keep in mind when those choices have been made for convenience and when they are dictated by something observational. Okay. So this is the hierarchy of scales that we're going to encounter. And I would claim that all models of string theory, string inflation, all the controlled ones I know of, are formulated in this setting. Okay. Okay. If you have counterexamples, we can look at them. But this is usually what's done. Yeah.
There are some problems. We are trying to think of inflation as an effective field theory.
Yes.
And we had some problems, so we want to know the UV composition of it. So it's like what are the realizations of the problems as in the effective field theory?
Yes.
In the higher dimensional theory?
Okay, so here I'm just trying to sketch out basically what we are supposed to expect later when we actually gonna try to construct these things in string theory. So just a priori, we expect these different types of energy scales to play a role. Okay, and we might worry that the UV sensitivity and the ether problem and also those kind of things might be associated with one or the other of these scales. Is that what you were asking earlier?
Yeah, I mean, I was trying to understand if we have some problems in the lower dimensional theory, how is it reflected in the full theory, like in the string theory?
Well, I think this is roughly what this whole lecture is going to be about, in some sense. Yeah. That from the bottom up, I was saying that any UV completion of inflation or generic UV completions of inflation are UV sensitive, so sensitive to high scales. Now we're going to try and do it in string theory. The string theory has an additional set of higher scales with concrete physical meaning, geometrical meaning, and so we can see which of these scales will impact our low energy for the effective theory. So I'm just showing that to you now, so you can keep an eye on these different scales. Okay, so this is the set of scales to be expected for the effective theory. What's the set of fields? What are the set of light fields? Of course, you know that when you compactify, you get moduli. So these are zero energy informations of the compactification. Therefore, they're massless fields for the effective theory. And since they're massless, I should say, at classical level, and then they typically gain potentials by quantum corrections. But since they're massless at tree level, we should expect them to be part of our spectrum in the effective theory, okay? Because we want to keep everything below some cutoff scale, and of course all the massless fields, will be part of the effective theory. So the most important fields to consider are these moduli, which at lowest order, do not have masses and have. In particular, you might hope that these are the fields that will drive inflation because they have some flat directions at some order in perturbation theory, okay? So which are these fields? So first of all, typically the size of the compactification, the overall size. You can show that the vacuum Einstein equations are scale invariant, okay? And so this is often a universal modulus that we have. The dilaton itself is also a modulus. It's even a modulus, of course, in 10D, and it remains a modulus in 4 dimensions. Then we have some metric moduli, so the Kähler moduli, which are generalizations of this volume modulus, and then complex structure moduli, basically shape deformations of the compactification. We can have axions, 4-dimensional axions, from the dimensional reductions of P forms. And then we can have grain moduli if we have some local sources in the compactification. Those local sources can move, and this motion of these local sources is associated with scalar fields in the 4D effective theory. Okay, so these are the sets of scalars that we should be expecting to see, and each of them in principle is an inflaton candidate, but each of them also is a source of trouble for the inflaton if it doesn't have suitable dynamics. Okay, so these fields are kind of a mixed blessing. Okay, they give us plenty of inflaton candidates to consider, but also if they aren't suitable for the job, they can be dangerous, and we need to control them. And so it's a double-edged sword in some sense. Okay, and then finally, the effective theory would be characterized by some spectrum of states, yeah, certain mass scales for each of these fields, and then in particular, and some set of interactions, kinetic and potential interactions between all of these fields. And so just a priori, you might expect, some kind of pattern of this spectrum of states. And from the bottom up, we have given names to these different patterns. So for example, what most cosmologists or inflationary theorists for decades have been considering is this kind of situation, yeah? Where you have a single light field with a mass that is smaller than the Hubble scale by this hierarchy of the eta parameter. And you're assuming that this desert of nothing else up to very high scales. And here, what I'm distinguishing high and low scales by the scale of my measurement, which is the Hubble scale. So everything lighter than the Hubble scale is considered a light field. Yeah? In particular, everything lighter than the Hubble scale is quantum mechanically active during inflation, produces fluctuations, contributes to the CMB, and so all of those things should be part of our spectrum. But everything above that scale, can be integrated out, and it will just affect the low energy couplings of these light fields. Okay? So that's what people typically have assumed. People have also looked at this situation where there are more than one inflaton field in multi-field inflation. And then more recently, and partly inspired, I think, by string theory and supergravity and supersymmetry, yeah, people have also considered the situation where there's a clustering of states with masses of around the Hubble scale. Okay? And this is kind of nice because it's actually a rather generic prediction, I think, of spontaneously broken SUSY. Yeah? So supersymmetry, of course, if it protects fields from radiative corrections. If supersymmetry is exact, they do not receive any radiative corrections. And then during inflation, supersymmetry is spontaneously broken. Yeah? But it still means that supersymmetry protects the high-frequency contributions to loops. Yeah? So if you think about the cancellation that you get in supersymmetry to the mass, for example, there's a cancellation between a boson loop and a fermion loop. Yeah? If the world was supersymmetric, this cancellation would be exact. The high frequencies, in fact, you don't feel the expansion of the universe. There's no curvature effect. And so this cancellation still occurs. Okay? But at low frequencies, you feel the effects of changes to your propagators from coupling to the Sitter curvature. And supersymmetry will be broken, and this cancellation will be imperfect. Okay? And the size of that imperfection is precisely set by the curvature scale of your background space. In Minkowski space, this would be an exact cancellation. In the Sitter space, there's still partial cancellations for all the high-frequency modes, but no cancellation for modes that are smaller than Hubble. Okay? And that's why you're generating these masses from radiative corrections of order the Hubble scale. Okay? Another way of saying this is part of the supergravity eta problem. Yeah? Supergravity eta problem tells us that every field wants to live up here, and we actually have the trouble of explaining how it is that some of the fields are light. So the generic situation is that everything wants to cluster here, and we typically face the challenge of explaining why some of these fields are light. Okay? So it's interesting to consider this second class of things. They have interesting signatures, in fact, in the CMB. I won't have time to discuss this now, but we can, if anybody wants to know, we can discuss what happens if you have a clustering of those fields. Okay.
So, last class, you said even for single field inflation, you will have this effect that during inflation you actually break SUSY,
yes,
etc. You're saying in the last class you have many fields. Is that right?
Many or one, at least one. I'm not making a big point about them being many.
Okay.
To study the phenomenology, we just consider a situation where you have two fields, one very light and one very heavy. That's the easiest one to analyze.
And then the expansion of the universe is breaking SUSY anyway, and you ask what does that mean for the lighter field?
Yeah. The point is that because these fields have a mass of order the Hubble scale, yeah. If their mass scale is less than 3 halves, 3 over 2h. Okay? That's the condition for the field to fluctuate quantum mechanically. So that then will mean during inflation, this will receive super horizon fluctuations. Okay? And if this field then couples to the inflaton, those things can mix. Okay? And so that mixing can have signatures. For example, it affects the squeeze limit of the three-point function. Things like that. And the squeeze limit of the three-point function will get a scale dependence that depends sensitively on the mass of this guy. Things like that. So you can actually see. You could use the three-point function as a particle detector to detect the mass of these guys.
Yeah, I've just understood it wrong. So, are you saying that inflation will necessarily break SUSY?
Sorry? Yeah, spontaneously, yes. positive vacuum
does
energy.
low scale SUSY work ever? Because, I mean, if inflation does break SUSY, then...
Oh, but it breaks it spontaneously. So you imagine, remember the inflationary potential has some large vacuum energy and then some zero energy or very low cosmology constant ground state. Okay? So during inflation, you're sitting at large EV, where SUSY is spontaneously broken. But then after inflation, you reduced your field value and you're now sitting at the global minimum. And at the global minimum, if the potential energy is zero, then SUSY is restored. So it's only broken by a small cosmology constant today, which is
Okay.
so that's why you have to break it in addition. So it's in addition, then you have to have some explicit breaking of some other thing that explains why we don't see a supersymmetric world at the TIB scale.
Why and scaling is the same
Well, as a Hubble scale? Okay, so this is what I was trying to say in words from the meeting. So in Minkowski space, yeah, you know, if you have, of course, because there's the symmetry between fermions and bosons, and they have two contributions with opposite signs. Okay, so you know that in Minkowski you have this cancellation. Well, if I now put the same theory in the Sitter space, yeah, this space now has a different, you know, the space-time has curvature, and the curvature scale of the Sitter space is given by the expansion by the Hubble scale. Yeah? But at very high frequencies, you're far inside of the horizon, so the effects of curvature are small. You're reducing to flat space if you're very deep in the UV. Okay, so very high frequency modes. But here you're integrating over all frequencies. Yeah? So the very high frequency modes will still experience this cancellation because they do not know that, like us now, we do not know that we're living in an expanding universe in this room. Yeah? And so you do have to go to frequencies of order the Hubble scale, yeah, in order to perceive the effect of space-time curvature. Okay? And that will then change. These propagators will then have some coupling to the metric. Okay? And it will change these propagators, each of them differently. And this cancellation won't occur. Okay? So for that reason, then you get, what you see, yeah? you get a remnant contribution to this sum here, which is about the Hubble scale, Hubble scale square. Okay? This is a very rough argument. You can see this more explicitly. Okay. Okay, so then the goal typically is, you know, I've described to you the typical energy scales, typical fields. So we want to look at these things and derive the spectrum of states and their interactions. So we need to study quantification and modular stabilization. So let me just highlight some of the common challenges are that, as I said before, modular stabilization in fact does not decouple from inflationary dynamics. And it's in fact hard to keep the inflaton light. Modular stabilization means I want to give lots of these fields masses much higher than the Hubble scale. And the challenge is, why don't I raise the masses of all of the fields? Yeah? You know, you have to worry that the same mechanism that gives masses to some of the fields will also try to raise the masses of all of the fields that I'm trying to keep alive. Okay? It's hard to create this things happen more democratically often. You don't engineer for some asymmetry in the mechanism. Okay? That's why sometimes local sources were a nice idea, because you thought maybe the local sources, you know, have a distinguished character and they operate differently as all of the bulk moduli that you're trying to give masses to. So it's typically hard to engineer this hierarchy between a light field and the rest of the moduli. And then why just one field? You know, maybe once you do engineer that hierarchy, you know, it's also, since you have many of those moduli, you can also expect maybe that many of those light fields. But then if they all quantum mechanically fluctuate, you know, it's hard to, they will all determine the inflationary phenomenology. It just becomes a technically hard problem to track. Okay, so I have halfway through, but not halfway through my slides by any means. So we'll see.
You do have a discussion session at the end of it.
Yes, yes. So I will have to navigate through this somehow, yeah, because I think there are 41 slides or something. Yeah, so I'll try to do this maybe by skipping some things, but without creating too much hectic. We'll see how that goes. Yeah. So maybe this I'll just be a little bit loose on. This is something I was really going to play while coming here, which is this nice set of lectures by Frederick Denner, the Zoosh lectures, where he's describing in quite a bit of detail how to construct explicitly string vacua. I think at the beginning he says that his goal is that at the end of the school every student can create their own string vacua. He gives it all geometrical tools and all. Pretty formal, much more formal than I could explain it to you. But he also has these nice qualitative arguments at the beginning of these notes, where he tries to explain why you should be expecting string vacua to be dirty and complicated. Yeah? And you should not expect the Sitter Vacua to pop out just anytime you look at the system. Okay? And so the two arguments that it goes through is, one is called the Dine-Seiberg Problem. The second one is the Maldacena-Nunez No-Go theorem. Let me very briefly sketch Dine-Seiberg because I kind of like it, or come to like it. So imagine you have a modulus rho, which might be the compactification volume or the inverse string coupling, okay? Which means that for both of these cases, rho going to infinity corresponds to the weakly coupled region. And then and in particular, the zero potential at tree level. Because by definition, that's what it means to be a modulus. And then quantum corrections generate a potential which satisfies this limit that at weak coupling this zero potential. So then there are two possibilities that this tree, that this first order, that either it's approaching zero from above or it's approaching zero from below. In one case, you get a runaway, in the other case, you push towards smaller values of the modulus, which is the strongly coupled region. So in order to stabilize this modulus, you then have to include higher order terms in this expansion. And so then you can expect in these two cases to generate a minimum. Okay? But then almost by definition, since you had to include higher order terms to generate a competing effect, competing force and have a minimum, either these higher order effects are small and not important and therefore won't generate a minimum like this. Or when they are important, they're by definition almost in the strongly coupled, or close to the strongly coupled regime and not completely. Okay? So that Frederick was rephrasing it as, when corrections can be computed, they are not important, and when they are important, they cannot be computed. Okay? And Dine-Seiberg were conjecturing that maybe the string vacuum we live in is important. Not maybe, actually. They were saying it's probably strongly coupled. Okay? And we won't be able to compute precise properties. Yeah? Of course, people in the meantime, especially including Sandeep, have found partial ways around this. But it's still something that looms in the background, because in KKLT, for example, you're not winning parametrically, but you're winning, numerically. You're finding you can stay, you can't stay parametrically far away from this strongly coupled regime, but you can arrange things in such a way that you still, because this argument, of course, is just an order of magnitude heuristic argument, and so you might think that there are examples where this does not have to be satisfied. Okay, but it's just something you can say before even doing any work. And the second argument is just a theorem by Maldacena-Nunez that showed that if you consider d-dimensional gravity without any higher derivative corrections, just Einstein-Hilbert, coupled to an arbitrary set of massless fields, so these could be scalars, p-forms, gauge fields, whatever you like, with positive kinetic energy, zero and negative potential, then they show that there do not exist any non-singular warped compactifications to the sitter. Okay? So this is not terrible because string theory immediately violates the conditions of their theorem. Okay? String theory, of course, has higher curvature corrections, and it has singular negative tension, O-planes, okay? But it still tells you that somehow these ingredients have to play an important role, and you have to understand those things, and it's not the simplest thing that you throw into the box that will give you the sitter back here. Okay? Okay, so these are the two things that he describes a bit more than I had time to do that now. For why you shouldn't expect a rose garden, and things to be very simple when you do the sitter. The sitter is still something that is hard to do in string theory. Okay, so what I wanted to do, again sometime, is describe a little bit in more detail how this works in type 2B. And so I gave you the original references here. So okay, just this I do very quickly because I'm sure all of you know this. This is just textbook facts about type 2b. These are the set of massless fields. We have a metric, a dilaton, an NS3 form, and Ramon P forms. Okay. It's also convenient to redefine the fields and first of all rescale the metric so that later we will immediately be an Einstein frame and don't have a non-trivial coupling between the dilaton and the Ricci scalar. We can also combine this this RR scalar with the dilaton to form the axial dilaton. We can combine two of these three-form fluxes into another three-form flux, the G flux. That's going to play an important role. And then there's this complicated combination of fluxes that we can write in terms of this 5-form F. Okay? And then this, in terms of these variables, this is the action at lowest order for type 2b. Okay? There will be alpha prime and G string corrections that we might have to consider later. Okay? And so these are just kinetic terms for all of the different fields. And I've suppressed some Chern-Simons contribution. Okay, and then finally, of course, we can have localized sources, D-branes and O-planes. And here I've just given you again what the action is for a D-brane. Okay, so let's just, as a very simple example for how moduli arise in this, let's look at dimensional reduction in this setup. So imagine you have the following ansatz, where this is the 10-dimensional line element. It's a product of the 4-dimensional line element and the 6-dimensional line element. And I've multiplied the 6-dimensional line element by a factor that depends on the position in 4D. Okay? And this is then called the breathing mode of the compactification because it isotropically rescales, locally rescales the size of the compact space. Okay? So that's a measure of the local measure of the volume of the compactification. And then this metric here is a reference metric with fixed volume. Maybe unit 1 in string units or something like that. Okay, so then, but if you take this ansatz and substitute it into just the gravitational part of the action, you can then perform the integral over 6 of the dimensions, okay? And you will be left with an effective action in 4D that has now the 4-dimensional Ricci scalar, the 6-dimensional Ricci scalar. So the 10D Ricci here, splits up into these two components, and it has a kinetic term now for this breathing mode U. Okay, so in fact the size of the compact space becomes a dynamical field in 4D, which is just one of the moduli. Okay, and in particular also we have identified, this is something I showed earlier. There's a relationship between this kappa, which is basically related to the string scale, G string, and the volume of the compact space. Okay. So we need to compactify to get a finite Newton constant and a finite Planck scale and so on. Okay? So here I've just copied again this 4D effective action. Another thing you see is that the 6-dimensional Ricci scalar gets multiplied by the volume basically, or by the inverse volume. Okay? So then depending on the value of this 6-dimensional curvature, you get different potentials now for this breathing mode. Okay? In particular, if this intrinsic curvature here is positive, you get a runaway potential. Okay? If the intrinsic curvature is negative, you get pushed towards small or strongly, and which as in Dine-Seiberg is the coupling where the limit where supergravity breaks down. And only for zero intrinsic curvature, which is the case for Calabi-Yau compactifications, do you have zero potential. Okay? And that's also consistent because for Calabi-Yau, this breathing mode is in fact a modulus, which does not have any potential at classical level, and this is what we're finding here. Okay? But even for Calabi-Yau, after SUSY breaking, typically you raise the energy and you're left with some runaway direction like this, and you have to stabilize that modulus. Okay? So typically, at least the breathing mode is unfixed in vacuum configurations, and that's this fact that I was citing earlier that tree-level supergravity has a scale invariance built into it. Okay? So therefore, we have to consider compactifications that aren't just vacuum and that have additional local sources or delocalized fluxes in the extra dimensions. Yes. But I could canonically normalize. Yeah, it's true. This U here is not canonical. Okay? I could canonically normalize this kinetic term here.
But it's singular. U equals 0.
U equals 0. Yes. Well, let's see. Yeah, what does U equals 0 correspond to here? Okay, so think about it. I don't think there's anything singular at U equals 0 because this metric is completely fine. In fact, U equals 0 is some sense an arbitrary point, which is where I defined my reference metric. Yeah. So at that moment, the reference metric has some given volume, and then finite U just tells me as I'm going away from that point in space-time, how does the volume respond? Yeah. So I don't think there's anything singular.
Usually log of the volume or something proportional to log of volume is the canonically normalized field.
Yeah, that's what I think, and this is what you see here. I mean, this 1 over U is the canonical transformation is the log. Yeah. I mean, the volume, the physical volume, the way I've written it, the physical volume of it is e to this.
Right. So shouldn't U itself have been, since log of the volume is the canonically normalized field, shouldn't U itself have been in your
Yeah. Yeah, we can check. I believe this is true. Let me go. Okay. So let's go one step further and ask for solutions to the supergravity equation of motion with sources. And so in general, these solutions are hard to find in a compact space. Yeah? So trying to find compact solutions, it's hard to find complex solutions. So it's a pretty major set when Giddings, Hashmer, Kretinsky were finding in this particular setting solutions. And so the answers were the following. They modified this 10-dimensional line element to include a warping. Yeah? So now I have another exponential factor multiplying these two parts of the line element. So now this factor here depends on the internal coordinate of the compact space. Yeah? So that here the line elements will change as I'm moving through the compact dimension. So that's what we call warping. It's a redshifting effect as I'm moving in 4D. And then coupled to this, there was also an ansatz for this 5-dimensional. For the 5 form, particularly the 5 form was parameterized in terms of the scalar function alpha and y. Okay? And so under certain conditions on the stress tensor of these local sources, they found solutions. And in particular, these conditions were things that were satisfied for D3 branes, D7 branes, O3, and so on. In fact, yeah. And so, but okay, I'm suppressing all of this and just tell you that these supergravity equations of motions are satisfied if these two conditions hold. So first of all, this warp factor here has to match the 4-form potential, alpha, okay? And the 3-form flux has to be so-called imaginary self-dual, meaning that the 6-dimensional Hodge operation on G3 returns the imaginary, okay? So these are therefore also called ISD compactifications that satisfy this imaginary self-dual condition on the 3-form component. Okay? So a useful exercise to do is to show that a D3 brane feels no force in this type of setting. Okay? All you have to do here is just you take the dBi action, dBi plus Chern-Simons for a D3 brane, dimensionally reduced to 4 dimensions, and you will find that the potential for a D3 brane takes the following form. It's normalized by the tension of the brane. That's just what normalizes the action. And then the potential depends on the difference between the warp factor, which will appear in the dBi part of the action, and this 4-form potential scalar function, which appears in the Chern-Simons part. And the difference between the two is the potential. So in ISD compactifications where these two are exactly equal, this cancels and gives you 0, and you get no force. Okay? It's very special about D3 branes, and that's why also D3 branes were kind of the starting point for brane inflation later, because in this type of compactification, they do not have a force, so you might think this is a natural way of starting inflation, where you want to have no force on a field to begin with. Okay? Yeah. So I'm just saying, yeah, so for higher dimensional branes, this will become more complicated because they're more complicated subjects than the fluxes. And And so it's a distinguished feature of 3 branes that they do not feel a force in this kind of background. Okay? You can check if you look at some higher dimensional brane and try to dimensional reduce this, you will get a force in this background. Okay? Okay, so this is a good exercise if you want to check your flex your dimensional reduction skills. You can try and confirm this. Okay, so now we have a compactification with finite value for the 3-form flux. And so it turns out that this creates a potential for both the complex structure moduli and the dilaton. Okay? And it's not so hard to see why that should be the case, because first of all, the dilaton appears actually in the 3-form flux. So by dimension reducing basically the 3-form part of the 10-dimensional action, it's natural to expect some kind of potential for all of the fields that appear in G3. Yeah? And in particular, also recall that the square of G3 that appears in the 10D supergravity action also includes the metric and the complex structure, in particular through this Hodge star. Okay? So that's a little bit of a harder exercise to actually really derive the potential for the dilaton and the complex structure moduli by dimensionally reducing the 10D action. And therefore, often it's convenient to describe this, in purely 4D supergravity terms. And so you can show that this same dynamics can be described by a superpotential for the flux, yeah, which takes the following form. And so here you just have to show that this kind of superpotential reproduces, first of all, the ISD structure of the solution, and then also reproduces precisely what you would get by dimensionally reducing this guy. Okay, so this was something shown by these people. And then also we have a Kähler potential, of course, which dictates the kinetic terms for all of these moduli. And here I've only shown the kinetic term for the complexified Kähler modulus, which is in fact a combination of this breeding mode part and an axion part coming from the 4 form. Okay. Any questions about this? This is a bit of a technical.
Intuitively, how do you get to this flux population?
Intuitively? Not intuitively, I think it's just a matching. Yeah? You try to find, I don't know actually, I haven't read this paper for a long time. But roughly the way I know would do it, if I had given my complete lack of memory of how they did it, yeah? It's just, so with hard work, you can show precisely what the 4D potential is from dimensional reduction, okay? And then you can try and reproduce that 4D potential, in 4-dimensional supersymmetry. SUSY isn't necessarily appropriate. Yeah? And so this just happens to be the potential that has all the right features. Maybe there's some other tricks that they have to actually get to the answer more directly. But the brute force way is just to do this matching. You do a 10D dimensional reduction, and you try to match that 10D dimensional reduction to a 4D effective supergravity. Okay.
That also brings you more or less. So you're SUSY tricks. So what you say is very good.
Okay. Yeah. I think this is mine is the low brow way, but I'm sure probably yeah.
And what is the 3? Is that important in the Kähler potential?
Crucial. Yeah, very important. You're going to see in a moment. Another exercise for you on the next slide, and you're going to see why that 3 is very important. Yeah. But you could ask how did I get this part? Yeah. This part I got because I showed you what the kinetic term for the breeding mode was. There was 12 over u squared and so on. Yeah. That 12, for example, yeah, will be matched to this. Here is the breeding mode. Okay. And so this scalar potential is in fact the scalar potential for the breeding mode. And so this will give me a kinetic term for the breeding mode, and that kinetic term has to match the dimensional reduction, which I already showed you. So this is something that you should be able to verify. Okay. But okay, now let's get to the 3. The 3 is crucial because now the scalar potential in 4-dimensional supergravity for all of these moduli is of course this, where I'm summing over complex structure, dilaton, and all the Kähler moduli. And because of this 3, you can now, another exercise is to show that this particular combination of derivatives and contractions with the metric is exactly 3, which means that this part will precisely cancel this minus 3w squared here, so that you're left with a potential which is now a sum that is only over basically over everything that except for the Kähler modulus t. Yeah? without the minus 3W. So the Kähler potential does not appear anymore the Kähler modulus does not appear anymore in this potential, so it's a no-scale potential. Again, we're finding this scale invariance of supergravity. Yeah. And this potential also you see is positive semi-definite. It's a square of dW, okay? And so it has a minimum at 0 energy, where all of these covariant derivatives of W vanish, okay? For all the moduli other than the Kähler modulus, okay? But the volume is still unfixed. Okay? So adding this classical flux does stabilize the dilaton in complex structure, but it leaves completely unfixed still the volume. Okay. And in addition to that, in perturbation theory, you can show that because you might think, oh, why don't I just add perturbatively a contribution to the superpotential that includes the Kähler modulus and leads to potential for the Kähler modulus. You can prove that in perturbation theory this cannot happen. Okay. This Kähler modulus T cannot appear in W. And the reason is very simple, because this complexified Kähler modulus that I was saying has as the real part the breeding mode, but it has in supersymmetry it's combined with the axion associated with the 4-form flux. Okay? That axion, though, has a shift symmetry. Okay? But by holomorphy, I'm only supposed to write something that depends on only T and not T plus T bar in the superpotential. Yeah? So T to the alpha is forbidden to all orders in alpha prime and G string in the superpotential. Okay? So then there are only two options for generating a potential. The one option is to look at perturbative corrections to the Kähler potential, where I'm not restricted by holomorphy in the same sense. Or to look at non-perturbative corrections to the superpotential. Okay? And so these two options were considered. This is called the large volume scenario, and this one is KKLT. Okay? And so I want to describe the second one. Okay? Okay, so let's go ahead a little bit faster. So far we have looked at classical contributions, but the volume was still unstabilized. Okay, next I'm going to look at quantum corrections to this and ask whether quantum corrections can lift the Kähler modulus. And so one example for such a quantum corrections is gauge theory effects on the world volume of a 7-brane. Okay, so here again I've given you a little exercise. If you consider a stack of NC, these 7 branes wrapping a 4-cycle in the compact space, then dimensional reduction will just gives you an SUNC theory in 4 dimensions with a gauge coupling that depends on the geometry of this 4-cycle. Yeah? Just like in the dimensional reduction that we had, and we were relating the Planck mass to the overall volume, the gauge coupling will just scale with the 4-cycle volume. Okay? But then you can import 4-dimensional SUSY technology to say that there's a superpotential generated by condensation of gauge genos in this theory, which takes the following form in terms of this gauge coupling G. Okay? But since we have this relationship between the geometry and this 4-dimensional gauge coupling, we can also express this in terms of the volume of this 4-cycle. Okay? And the volume of the 4-cycle, which is proportional to the breeding mode, is just proportional to T plus T bar. Okay? Which then tells us that this superpotential indeed will depend exponentially on this complexified Kähler modulus. Okay? So this roughly is how you get this superpotential from dimensional reduction of a 7-brane wrapping a 4-cycle and looking at the 4D effective gauge theory that you get on the world volume. Okay. But now this superpotential here breaks the no-scale structure and stabilizes the moduli, the Kähler modulus. In particular, at low energies, you can show under certain conditions that the masses that are given to the complex structure and the dilaton are hierarchically higher than the masses that you get for the Kähler modulus. So you integrate out those first, and you get an effective 4D description now for just one field, the Kähler modulus. Okay. So this flux superpotential has been chosen to be a constant, and the value of the constant will depend precisely of how the dilaton and the complex structure moduli have been stabilized. And you can analyze the potential in the simpler setting with just one field. Okay? Next exercise is to take these structures, calculate the F-term potential. You should find something like this. And then you should plot this for certain values of these parameters. Okay? And so when you plot this, this is what you will find. Okay? You indeed find a minimum for the breeding mode. And these internal parameters here W0A and so on have been chosen such that this minimum appears at a relatively large value in terms of the string, the string scale. In particular, what he had to do is he had to choose a relatively small value for this flux quantum, flux superpotential value of 10 to the minus 4. This W0 will be correlated with the scale of the minimum, at what, where this minimum occurs. For smaller values of W0, this will be pushed towards larger values, but for larger values of W0, you get closer to the strong coupling regime. Okay. But then this W0 also correlates with the depth of this potential, so you actually can't make it too small. So that's, again, this is kind of a reflection of Dine-Seiberg. You can't go too far away from the strongly coupled regime. Okay? Another little exercise would be to show that actually this minimum here is supersymmetric. Okay? You can just prove this condition at the minimum. So this vacuum we have found at this moment is a supersymmetric anti-de Sitter vacuum. Okay? Of course, next we want to describe inflation in this context. So we know, our universe which has positive vacuum energy, so you need to uplift. There are various ways people have proposed for this uplifting. This is often the least satisfying step in this construction because you're often explicitly adding by hand some SUSY breaking contribution. Yeah. Sorry, say again.
The volume stabilization happens only with quantum.
It happens not by classical sources. In this particular example, no. Yeah, in this particular example. You could add, and this is also specific to 2B. And actually, in 2A, it's reversed. As you can see, even by mirror symmetry, so you actually stabilize classically the volume, and then the complex structure is the one we worry about more. We can go through other examples. This is just the one that I want to do as a case study. Okay. Okay, so the very simplest way of doing this uplifting is to add additional local sources, in this case, anti-D3 branes. Okay? So remember, we proved already that in ISD compactifications, there's zero potential, and that's because there's a cancellation between dBi and Chern-Simons. Okay? But for an anti-brane, of course, the Chern-Simons part has the opposite charge, so it has a reversed sign. So where there was a cancellation for a D3, there will be a positive contribution for an anti-D3. In an Einstein frame, you can show you have to rescale by the volume, and so you get an extra dependence on the breeding mode. Okay? Which isn't so important. I mean, most importantly, you just add a positive energy contribution to this potential. Okay? And this leads to this metastable de Sitter vacuum contribution. You can prove that it always has to be metastable because you know that in the limit of asymptotic limit of infinite volume, you should be just reducing to 10-dimensional supersymmetric to 10-dimensional supersymmetric theory, which has zero vacuum energy by definition. So there's always a lower energy solution at infinite volume. Yeah. So then, therefore, these de Sitter vacua are always metastable rather than global minima. Okay. And so what inflation is in this context then is trying to destabilize this vacuum in a controlled way. In some sense, we don't want to have false vacuum, inflation where we're just sitting at this minimum, but we actually want to dynamically evolve towards this minimum, from some other de Sitter vacuum. Yeah. So now we have to make a choice because yeah, 5 minutes. Well, definitely. Well, it depends on. I can do a 5-minute version.
Yeah. But what I was going to suggest was that the discussion session, you certainly could get an hour to further elaborate. Okay. So you could organize it so that you at least have 5 plus half an hour.
Yeah. So actually, for this example, I didn't actually want to say all that much because actually I prepared these slides at 4 in the morning. I think you will be able to see that this was the last thing I did for this. So it's very schematic, and all I wanted to say about brain inflation, in fact, is it has an ether problem. Okay. But okay, let me say a few more things about this. So you now might add, how do I get dynamics in the setting? And I said earlier that because you worry about all these effects that we were describing, classical effects and quantum effects, give masses to these fields. And so if I consider now one of these moduli to be an inflaton candidate, why doesn't that field also get large mass? And so one way of trying to create something which has hierarchy is to introduce additional local sources, which might have a distinguished character. And so here the idea was to introduce a space-time filling D3 brane, which is point-like in the extra dimension. So it's extended along our four-dimensional world. And so then the position in the extra dimension will be, will play the role of the inflaton, okay? And so it will be, again, a modulus or a scalar field in 4 dimensions. And in particular, we're starting with a D3 because in this ISD setup, we have shown that this feels no force. So maybe this is a good starting point for inflation. By weakly breaking the ISD condition, maybe we can generate a potential, but we still have this underlying structure that maybe starts off with zero force. However, we also know that this ISD condition, in fact, is broken in a stabilized compactification, both because of this gauge-Eno condensation and also from bulk effects from the compactification. Okay, this GKB ansatz won't be satisfied, globally, and so perturbations to the geometry is in the UV, for example, will also break this ISD condition. So the question is, what is the D3 brane potential in this stabilized setting? And so here the upshot, as I said, is that it has an eta problem. And I wanted to show this from several perspectives. 2 perspectives, in fact. One is just from 10D. So if you look at the supergravity equations of motion and you combine the trace of the Einstein equation with the Bianchi identity, you can write down this following kind of master equation, which is an equation that has the Laplacian, the 6-dimensional Laplacian, acting on this combination e to the 4a minus alpha, which you should remember is precisely what appears in the potential for a D3 brane. So solving this equation indeed does actually give us the force that a D3 brane feels in this setup. But it has local sources, which first of all is coming from, one source is the imaginary anti-self-dual component of the flux. So if there are deviations from the ISD condition, they will source this potential through this equation. And then also in a curved space, there's also coupling to the curvature. And then there could be local sources coming from anti-branes, for example, that induce a Coulomb potential between the 2 branes. Okay? So this is an equation that tells us a lot about the forces on that brane. But in particular, if we want to study this in the de Sitter space-time, which is ultimately what we're interested in for inflation, then there's a relationship, of course, between the expansion rate h and the 4-dimensional Ricci scalar. And so putting this on the right-hand side, you could iteratively solve this equation. You find a constant contribution, which is the inflaton potential, which by the Friedmann equation is coupled to h. And you find a mass term, just by integrating this Laplacian, which scales with the Hubble parameter itself. Okay? So you did indeed find, just from this 10-dimensional equation of motion, a mass of order the Hubble scale, and therefore an eta parameter of order 1. Okay? So that's the eta problem. You're coupling to curvature. But I've written ... here, the extra contributions to the potential. For example, if there is a breaking of ISD, that breaking of ISD can also depend on the position of the brane. For example, this gauge-Eno condensation effect, it's very easy to see that will depend, in fact, where the brane is sitting. And so you have additional contributions to the potential, so those in principle can compete with the eta problem. Yeah? But at best, you will have a fine-tuned solution. So you might have extra contribution to the potentials that cancel, but as soon as you find one large term, this whole setup will just be tuned. Okay? So it's not something that naturally inflates for this reason. Okay? So that's in 10D. We can also see this from our 4D perspective, where the Kähler potential, in fact, gets modified because the brane backreacts on the overall volume. So imagine putting the brane in the compact space and then moving the brane around. Since if the brane is a probe, then the compactification is just assumed to be fixed. Okay? That's what we did earlier. But now if you allow for the brane has stress energy, you can calculate how that stress energy backreacts on the overall volume. And in fact, as the brane moves through the space, the volume will adjust. And it's in fact this non-holomorphic volume that appears in the Kähler potential. And you can show that just also by dimensional reduction, you can show that this non-holomorphic volume, in fact, is a mixing between the position of the brane, which I've called phi, and the Kähler modulus T. Okay? And And from that, you can then show that this also leads to precisely the same ether problem that we had in 10D. And similarly, but again, so since this brain now carries stress energy and it backreacts on the geometry, it will also backreact on the geometry of this 4 cycle that was producing for us the non-perturbative effect. Yeah? And remember that the gauge coupling of this non-perturbative effect was proportional to the volume of the 4 cycle. So if the brain is very close to the 4 cycle, this backreaction will be big. And yeah, but as the brain moves away, this backreaction will be smaller. And the volume of the 4 cycle will adjust, and therefore the size of the gauge coupling will adjust. And therefore the size of the non-perturbative effect will adjust. Okay? So that's the chain of logic, how dropping the probe approximation for the brain leads to backreaction on the geometry, but the gauge theory has been geometrized in string theory, and therefore this non-perturbative superpotential also will develop a dependence on the inflaton. In certain situations, you can calculate this, and you can ask what are the conditions on this 4 cycle to cancel this contribution. But again, it's only through fine-tuning that this cancellation leads to inflation. Okay? Okay, so I could stop here and then say more about this later if some people want, or okay, so I'll stop here.
Let's thank Daniel for the two lectures. And if there are questions, maybe 1 or 2 questions maximum. Good. There is none.
Okay, well, there'll be a discussion session, so we'll have a chance to ask Daniel more questions. But before we conclude this session, this is Daniel's last and concluding lecture, although there will be a continuation in some formal sense. And so I think it's been a really great set of lectures, and I'd like you to join me in giving him a very big hand again of appreciation here. And there's a small token of appreciation on all our behalf, which I'd like Professor Sudhakar Panda to give to Daniel, so that he will carry back a memory of his school. And it is the wheel you will see in the Konark temple. Oh, that's good. Hang on 1 second. The cameraman here, and I didn't have my act together. I just asked you for 1 minute of your. Just 1 second. Great. Okay, and 1 more. Excellent. Okay. Well, thank you very much.
Sir, wait a minute.
Oh, yeah. I was wondering where you are.